Hi class, this is your instructor. I'm going to be discussing about the initial phase where we come towards the linear programming gradually. But before that, we should have a concept about the feasibility region and how you're supposed to form all that through graphical analysis when we have two unknowns. So for instance, I say that you have a value x and y. So now if both are unknown, so you have to keep one as 0, the other you can find out easily. And just to give you a simple example, I would just say that, let's just say we have x plus y is equal to, let's say, 10. Now this could be also an inequality. We have studied inequality in detail in previous lectures. So this could be greater than or equal to 10 or x plus y less than or equal to 10. In this case, both of them could be some kind of composition that could be less than or equal to 10. So it could be, the value of teaspoons of sugar. We have done that in one of the examples. Similarly, that could be also the ratio of teammates, band members, some musical group, of some kind of a ratio for the composition of some product. Then this is basically another inequality which is greater than or equal to. Now, there's a concept which will be involved having both of the coordinates lying at the point of origin, which is this point. And the line could be having in this could be the real number line. For instance, is the negative infinity to positive infinity, let's suppose. But for the sake and purpose of graph, you can just have this, limited to some positive value and some negative value. And we usually try to avoid negative values so that we can have some defined, easy to gather feasibility region in this graphical solution. So if we start with this, then we can say that all lines are supposed to cross this, and our solution could be either lying below that or above that. Now if x could be, let's say, 0 and y is -1, that means that it could lie somewhere -1 to 0. So that means that this is basically limited by this point of origin. Similarly, I could do the inverse as -1 to 0. So that means now we are limited by -1. Now this is basically the intercept here. This is the negative part, and this is the horizontal axis, where I can say that this is limited by the intercept. So this can be limited within this region. Okay, so this is negative. But if, let's suppose, this was 0 at this point, so this cannot exceed, this cannot go, this region has to be limited within this part. So now, in order to determine whether the feasibility region could be lying beyond this point, we have to assume whether this solution is actually satisfying this equality or that equality. So now if I put both values here as 0 and 0, is it satisfying this linear equality? No, it is not, because 0 cannot be greater than 10. So we cannot assume for this particular situation that for this particular equation that both the points are at the origin. So our feasibility region cannot include the origin in this case. Similarly, if for this particular condition we can have 0 plus 0 less than or equal to 10, that means that it is satisfying this inequality. So then for this particular equation, we will have a feasibility region. Feasibility means, or it is derived from the English language feasible, which means that it is something practical, possible. So then we can include this point of origin. And now this would be limited by this, then we can have various values to y. So if -1 and then it could be to 0. Now if I assume y to be 0, and x to be of some value 2. Again, that can be less than 10. So that means that all of this region can be before 10, all this region can be feasible for us and for our solution. But if we have y as, let's suppose, 2, now if I put 0 plus 2, that means that even before minus 1, if this is 0 to 2, then it can go till 10. If x I take as 0, then this can actually go till 10. So from minus 1 to positive 10 can be included, but then that has to be reducing. So our maximum point can be here, and it can have a maximum point in this. So this all can be included in the feasible region in this case. But sometimes the solution is not simple, because we can have 9 plus, or we can have x as 9, and we can have y as let's say, in this case, let's suppose we have some value 2. So now in this case, this would be 11 less than 10, so this would be incorrect. So in this case, we cannot have y2 if x is 9. So that means we have to be placing the values in the equation to find out whether the feasibility region can be for a particular situation. And that is the concept of feasibility region. Now, why are we doing this? This is very important because this concept originated from trying to find out the unknowns, which were fewer in a quantity, for instance, 2, 3, which were practically possible. In one of the lectures I've given about simplex method, you will see that this is what the technique is usually employed. It has been evolved from the central idea presented by Danzig in 1947. This was primarily an unsolved problem, which was solved by a student, and the reason was that there are many things that we want to look at, like for instance the trajectories of the missiles, and even anything that you're directing, for instance like rockets, and for even the flights that you're having, you just need to have a trajectory. So for those you need linear programming, because you have a lot of unknowns in that case. Similarly, we need to find out how to allocate resources. So then there are unknowns there, and we need to maximize or minimize them. So how to maximize profit and how to minimize the cost. And similarly, we need to also see in situations where there's algorithm involved. There are interactive websites where there's a requirement. For instance, a person needs to have some kind of evaluation done based on their emotional well-being. They want to have some kind of a session with someone where they are required to, let's suppose have some intuitive testing, and they are given certain questions to answer so that a particular person can be allotted to them. Some patient needs a doctor, some psychological evaluation, and the psychologist is required. Now, the kind of problems that a person can have, that will lead him to a particular psychologist or a doctor. So for that, you need a set of questions. So they could determine the requirements. So that requires another kind of algorithm. Now there are unknowns, so a lot of unknowns. For those unknowns, you need computers. But for simplistic unknowns, which you can do manually, especially in the simplex method, you will see that it is required that first of all, the concept is feasibility region, how you're supposed to graphically allocate and find out. Then it is more about resource allocation, and then you can come towards the constraint, whether in a given situation, if you have a limitation, then you can, draw parallels. And then there are different situations where you can adapt them. I'm going to be starting with this chapter. The book is by Stefan Costinoble, and it's 7th or 8th edition, whichever that you have. The latest is all the better. And the book's name is Finite Mathematics. It's an excellent book. I wish that you would read this chapter through, and we are going to be studying the intro part, which is chapter 5 for linear programming, but the basis has to be started from the graphical analysis and feasibility regions and solutions and point of origins, where we require them and where we cannot have them. Because for instance, if this is less than equal to 10, then x plus y is equal to, let's suppose, 0 is less than 10. This is how you're going to be writing this whole equation. And then we are going to be taking a few examples before I move on to the lecture where I'll be attempting a few numericals. But in this lecture, I'm going to be primarily focusing on how to go about the, studying about and analyzing the problem in itself. So then we can move on to the practical problems in the next round of lecture. So let's just begin with the concept. Okay. Now I have to rub this off. Class, let's just begin with the. Now, this is a linear programming chapter where first section would be about graphing these linear inequalities. Then we go about one example from 5.2 because 5.3 and 4 have practically been done in other lectures. So we're going to be focusing on the examples that in the next part 2 of this lecture, I'll be attempting a few numericals for your better understanding. And let's just move on to the case study pertaining to the diet problem. It's very similar to the example that I've already given to you. It talks about the Galaxy Nutrition Health Food Mega Store chain. The central idea in all of this is basically about the clients having constraints such as budgetary constraints, and they need to have a diet plan which is tailored to their nutrition and nutritional requirements, basically. So how do you construct such a constraint oriented website where you can have requirements like weight and diet preferences and for quality and for cost effectiveness within that, and you can have the whether it is about a customer who is more cost conscious and the other one then who is more quality conscious, and then there are certain ones who are calorie conscious. So in order to incorporate all this can be very complicated. Therefore, it is required that we have certain algorithmic programs with us. Now, this is just one of the applications. I would like that you go to this website, which is wanermath.com, and it says linear programming. Oh, sorry, the book's name was actually, I think, about Stephen Waner and Stefan. So now this is linear programming grapher and pivot and Gauss-Jordan tool, and a simplex method tool. So now you can have both of them in this wanermath.com. So we're going to be looking at that in the next lecture about how to go about studying the Gauss-Jordan tool and the grapher. If it's automatically, then you can just have the insight into this. Now let's just go towards the introduction. Like I have already told you that there was Danzig who had this technique to solve in real life application. I'm going to be skipping up this part where they're just talking about who actually why this was required in the first place. Then you go towards the linear inequalities. Let's just look at this has already been studied in previous class lectures. You already know what an inequality is, how to form the equations where x and y are both assumed to be greater than 0 or equal to it. Now, usually we avoid to have negative values because then that would make the feasibility region, wider than we expect. Because if it is too wide, then it's difficult to have a, solid conclusion drawn based on this. So now these are just some of the examples that they've given us. Let's just look at one of the constraints. And there are three situations, which is they're telling you that what is a non-linear inequality and the other is linear, where it is parsed some sort of like a polynomial situation or multinomial. So we're not going to be going towards these. We're just talking about the simple ones right now, which is linear inequalities. Then there are other ones which are quadratic in nature, and so multiple solutions can be derived from this. Just look at this one. So this is 2x plus 3y less than 6. So what I was trying to explain to you is that either you keep one as 0, the other can be found. So if we keep y as 0 here, highlighted as y is equal to 0 in this case, so you can have x as 3. Now let's just assume that x in this case is 3, because then you can just divide x by, by finding or placing it as equal to 6 by 2. Similarly, you can have x as 0, and then y can be found as 2. So the coordinates could be originating as 0, 0, and then you can just simply place the values here, and yes, it can be less than 6. So this point of origin would hold. And now if you see, this is the point in the graph where one is 3, the other is 2 in this case, and the maximum values that both can reach. The reason why we place 1 as 0 is that that would give the maximum value to the other variable. Okay, so that's just a simple example. Now we're going to be, talking more in terms of what is feasible and what is the solution set in this case. So if you take this possibility now, what could be the number of solutions lying for this particular equation? We take 0, 0 as the point of origin, because now this is, but not every time, because this equality could hold if it was greater than 6, and for that equation you can't really have this as point of origin, because they will be both, and over at that point the feasibility region will be lying somewhere up here. And in this case the gray part is reflecting outside or lying outside the feasible region, and this is half plane. This part is half plane for both x and y in this case, where now all these values, this blue is basically your entire solution set, because you can have values in terms of the half plane, and since anything is less than this, so they could assume the negative values as well. So for less than means that all values lie under this. So now you can see that they have already stated this point, that it is a solution and is not on the line every point as 0, 0. So all points are not lying on one line, it's just going below. Similarly, we have another reason to this, and they've given a detail of what I've already explained to you in the beginning of the lecture. You can just simply read upon it. It's just any point above the line is directly above a point on the line. Now, just a similar assumption that I gave you in my lecture, that if you take any other point which could be satisfying this equation, you can just assume that this could be lying as part of the feasible region. But if it is not satisfying the equation, then you would limit your equation below that or aside or separate from that. Now, the test point is basically where we would be, blocking out some part and putting some values inside this equation. And in this case, they are telling you that the test point procedure we described gives us an easy method that would be including some regions and excluding the other. This has already been explained. Now let's just move to another example. We are, as already informed to you, that we are going to be discussing two variables, and in simplex method we can have more than that. So there's okay, this part I'm going to be doing in spreadsheet if possible. Now let's just see this part. So we have to sketch the line. You already know how to sketch the line, and this point now again. Does it satisfy the solution for greater than? Usually it does not. So had it been, maybe less than 5, then it would have been able to satisfy this equation. But now it says it is greater than 5. So now for this particular equation, you cannot have this point. So that means that you cannot include this point. So your solution set will not be satisfied by having the point of origins included. So the shaded portion would be reflecting that this is not part of the feasible region. So our solution set will be lying somewhere above that, because our line has been marked here. So from origin to upwards we cannot really include. If 0 is not satisfying, then other numbers would also not be satisfying, cannot be greater than that. Before we reach this line, no number can yield an answer which is greater than 5. Now let's just look at these values. So also know that when you're sketching the regions, try to minimize or have a common divisor which can make an answer very simple. And in this case, if you see A and B, they both are almost the same. So it is going almost, do make sure that the variables, if you are given a number, and for this you try to keep the variables on one side and the number on the other side. Don't try to straddle the variables along the left hand side and right hand side, because that will not give us the required response. So now 6x minus 4y is less than or equal to 12, so you just have to divide it by a common divisor, and in this case that would be 2. So 2 3s are 6, 2 2s are 4, and 2 6 are 12. So this and this is the same thing. And in this case we'll assume that y is 0 because it's just been given a 1 solution. Here y is greater than 0, and then we have single-handed equations where you can just assume that x is either from -1 to 0, or you can just simply draw one part to understand, then make sense of the other. For individually analyzing, you can see that now x has, now what value you can have by putting y 0. So in that case, your intercept will be 0 in this case. So x would be 2. So in this case, the value should be somewhere as x, and the graph is figure 5. Make sure that you read the relevant graph, and this is figure 5. Okay, so now in this case it would be lying somewhere here after the solution set has satisfied the equality. Why we're doing it, you should be very careful about that, because if it is not satisfying the equation, then we cannot have this feasibility region. But if it is satisfying the equation, then we can begin feasibility region with the origin. So now we have x as 0, and then you can see that y is negative, and it's -3 in this case. As you can see, this is -3. So now this comes to this part, and from this it can go upwards. This is slope. Some equations you will see that they are in terms of x and y, where the number has not been given to you. So you can just simply determine one equation in form of the other equation, and you can't put a 0 in that case. So in that case, x would be determining the slope of the intercept y. Now this is the solution set for this case, you can see. Similarly, we can look at this equation. This is just the same. It will be again the same as previous equation as C, figure 5 for that. Now look at figure 6 for part C, which is x is less than a minus 1. So if this is the point of origin, can this satisfy our equation that with both coordinates expressed as 0, but since we don't have a y here, so it's just 0 is less than minus 1 won't be possible for us because 0 is greater than minus 1, right? So we can't include the origin in this. So if x is minus 1, it is limited by our y, right? And this part will be limited by the y-axis, and this is minus 1. So our solution set will be lying below this part. Now again, next part is where y is greater than 0, and this is figure 7, and this is part of this example. As you can see, this is y is greater than 0 is part D. And okay, now in part E you can see that this is greater than or equal to 3y, where we're going to be expressing one variable in terms of the other one, so that if I express it as y, then y is okay. When you are moving both the variables on the other side, you can also change the equality, but in this case you're not changing the equality. It's just y is 1 by 3 of x, and again 1 by 3 of x is greater than or equal to y, and then if it has a boundary line of x is equal to 3y, so now you can have this equality changed into, from inequality changed to equality, where y is equal to 1 by 3 of x, and then you can draw this where x is representing the slope, so that 1 by 3 is 0.33 something decimal, but it is less than 0, so the point of origin is 0, and it will be slightly more than 0. So, but it will be affected by the slope, because that is determined by x, so we don't know x at this point. So we're just going to be drawing the slope but it cannot be 0. So if you just see the graph here, and this would be figure 8. Now you see that this is y is 1 by 3 of x. Okay. Now, so this is point is having some kind of a slope b, like y is equal to bx, and since we don't have an intercept at the moment, we can assume the intercept to be 1, but just to see if y is 1, then can it satisfy the equation? But this would not be possible in this region, because it already says there is some decimal fraction of x, or it could be more if x is let's suppose 100, so it could be way more, but at this point 1 is equal to 1 by 3 is hard to prove, and they have already stated that we cannot choose the origin as a test point in this case, because you can't keep both the values as 0. As you can see, you can't keep it as 0 and 0, so you can't have a test point really, and you can't assume x as 0 in this case, because this whole equation would be 0 in this way. So if x is greater than 3y, which means that y cannot be at that point 0, so it has to be some minimum value 1. So, but if you have a minimum value of 1, and given that x can be 0, if assuming that x is 0 in this case, would be false notion, so we cannot really have both of them as 0, or one as 0, the other as 1, because we have one expressed in terms of the other. So if one is 0, the other would automatically be 0, so both of them cannot be 0 in this case. And so similarly, we cannot have one as 0 and the other as 1 also. So that means that this feasible region can be less than this entire value of 1 by 3x, it cannot go above this, because see, this is 0, it can't be 1 in this case. For instance, I say that y is 1, that means that if x is some value, so some decimal value cannot relatively lead up to this point. So you have to go below the solution set from the point of origin onwards. Although x can assume values, but in terms of y, those values would be expressed in decimal for 1 by 3. But if the value x exceeds to a greater point, then the slope would be dependent upon the value of x, and this part is more than the value that y can achieve. So we can have the slope drawn on either side, because x can assume, in this case, negative values as well. So x has to be always greater than y for y to have a value. Now you can just assume, this is all based on assumption, and they say that these assumptions are false. So this was the previous solution, you can just go over that. Now we have this interesting part where they've sketched the region of points that satisfy both the inequalities. Now if you have 2x minus 5y is less than or equal to 10, in this case again you can have one equality as, let's just find out what y is. So y comes to about minus 2 as reflected in this part, minus 2. But if we keep both of them as 0, can we have the solution originating from origin point? Yes, we can actually, because 0 minus 0 can actually be less than 10. Or any negative value can also be less than 10. If x is 0, then we can have y as 1. Yes, we can also have 0, 1 in this case. So, so y is 1, and this will be minus 5, which is less than 10. So we can have x 0 and 1 also point of origins. We can also have 0, 0 as point of origin. And from a minus 2, now how do we draw this whole line? You see, then we can keep this as 0 and then x as 5. So x is 5 here, so minus 2 and 5, then you can just simply extend arrow where this would intersect with the second equation's feasibility region, where y would be 4 as 8 by 2, and x would be 8. So this would be a greater region. So where both the points would intersect. But sometimes it's very hard for equations to intersect, as you can see in following equations. Like I told you, to assume that both can be 0, it can be less than 10, and again both equations are satisfied in this case. And similarly, you can keep assuming for 0, 1, 0, 2, 0, 3, where the point where they would satisfy either of the two equalities. So for, let's say, 0 and then it is minus 25 is less than 10. You can have any value here because it's a negative sign. It can just go any value. But but this is a positive value, so you can have a limit to this till 4. So that means your feasibility region will be limited to 4 in this case. You can't have a higher value of 5 because this would violate the condition for this equation. And again, you can have not just necessarily these points, just to explain, you can have any other assumption that you want to show that would not be passing the test for satisfying this inequality. So for instance, if they've taken that x is 5 and y is minus 1. So for 5, this becomes 10 minus 5 is again 5. This is 10 and minus 5, and then this is, okay, so now for this case, if you see this is minus 5 into minus 1. Had it been a positive one, they would have satisfied the equality, but this is minus 1, right? So this is minus minus as a plus, so it comes to about 15, which is greater than 10. So this would not be satisfying this equality, but this would be satisfying this equality, because this negative would not be cancelled out. And so you can have for this equality, but not for the other. So if it is not for one equality but is for the other one, you just do not want that, and you try to actually finish the negative signs for simplex methods especially. So similarly, you can just look at these solution sets also. Like I told you that sometimes the point of origin can have interesting results. I would like to go towards a problem where even if you see this one, you can just see that sometimes solution set is not possible because the entire region is not included in this. I would like you to look at this one and give me your comment on this. And why is this an empty solution? There's no solution for this. This entire area is gray in this case. Moving the horizontal line, so this is basically your figure 11, and I would like to see that moving the horizontal line at y is equal to 6 down to y is equal to 2. So now we have figure 10. We have y 6, and then we can move it to y equal to 2 somewhere here. Maybe down, like they have moved it, like down. So this is not actually intersecting at this point, but way down. So in that case, this is point below the point C actually. So graying out everything above it. So this is basically empty, that there was nothing at all in the solution set. So now you can y is 2, and you can just simply see that the value, let's suppose, was coordinates was 0 to 6, and then 4 to 6, and now see for point C, this is 3 to 3. So these are the coordinates that they're talking about here. Below the point C now. For C, this is below C. And now you just simply put in the values of y is less than 2, y is less than or equal to 6, y is less than 2. So you have to see that this has to be, some value where it has to be less than 6. But if it is, let's suppose, some value which is not satisfying that, now how come that could be? Because if it is, let's suppose, 3 2s are 6 minus 2, again, that would be less than 6. But if it is 3 4s are 12 minus 2, that would not be less than 6. So for having a coordinate of x, it also depends upon the coordinate that you're having. And y in this case, for that particular situation where we're discussing this example, we would not be having for this value which is less than 6. If x is 0, in this case we have y as 6. But for having it as 2, the solution set is just this part. But if we have as 2 down below, then it would be lying outside the solution set. So you cannot actually have a satisfactory solution to this problem. See, this is the solution set. So if you're lying somewhere below the solution set, it will be an empty solution set. And there's just one point. Okay, I would like to various methods for studying about the extent to which we can find some feasible region, and then from that we can derive the solution. So we can bind them together or not have any closure to that. So infinitely in one or more directions are unbounded. So I already told you that in the real line we have negative infinity to positive infinity. So this could go either way, and there would be a very large solution lying outside the solution set, a large area, and it will be very difficult to go towards some particular conclusion in this. Okay, this is something which is very simple. You can just go about having to study about various feasibility regions. I would like to particularly focus on 5.2, and these questions will be done in lecture part 2, and I'll be combining a few questions from here and one from 5.2. So I would like you to at least go over these examples where, okay, there's one example I particularly want you to interpret and see. Now that is, if I can just, this is all simple. Let's just see. I was talking about it at the beginning of the lecture about resource allocation. So if you can see, you can have various interesting shapes here. Okay, we'll be doing it more about the unbounded regions and the questions that come forth. Now let's just see. Okay, this is an example. So now you see that you are composing a ballad for violins and bassoons in your ballad. So each violinist plays a total of 2 notes, and each bassoonist plays only 1 note. And in this, basically, you just have to arrange the data. In order to make the ballad sufficiently interesting, you have to decide a minimum of 300 soprano notes. This is the again. Minimum means greater than or equal to, and least would also be, greater than or equal to. So it's just different terminology being used here. So give your composition a sense of balance, you wish to have no more than 3 times. Okay, when you ever meet a statement where it says no more than 3 times, so first of all, you already know that it's an inequality of, because it is no more than for one and it can be no less than the other. So one variable is going to be expressed initially in terms of the other variable, where they have assumed violinists to be, x as the number of violinists and y as the number of bassoonists. So if one is no more than the other, that means that one is less than the other. And in this case, as you can see that a violinist is x, and this is bassoonists are y. 3 times as y, so it's 3y, and you can have x, like here, 3y and x. But in terms of expressing, you can say that x could be, either, if you're placing one as y, the other as x, then you can have, x less than 3y, or it can be y less than 3x. Depends upon which you want to label as x and the other as y. There's no condition, but for the purpose of this example, like they have given us the understanding of what to take as x and what to take as y. If you see this equation, as I told you, then it is no more. So that automatically means that this is an inequality of less than in terms of one variable expressed in terms of the other. So in this case, you have bassoonist 3 and let's just see, either of whatever that you want to express as. So 3 times as many bassoonists, and this is the number of bassoonists as in terms of violinists. So the number of violinists, in this case, since they have taken it as x, we can have 3x, because now we have and y, which is the number should not be more than 3 times the number of violinists. It could be rephrased as that. Okay? So again, I'll read it that it is no more than 3 times as many bassoonists as violinists. So it means that the bassoonists cannot be more than the violinists in this case. So if bassoonist is termed as y, then y in this case cannot be more than x. So this is 3x. Now you can have it placed on the other side, and when I told you that when variables are moved towards the other side, the inequality is changed to greater than or equal to 0. So the total cost is another constraint. Let's just move on to this one. It says that the charge, y will charge 400 and x would charge 200. So now 200 and 400 would be your cost performance. So you need to have a value which can be interesting, but it should also be cost effective. If you try to again find the feasibility region, it would involve simultaneous equations. So we are given a few equations in this. So for instance, one is to minimize the personal cost, one constraint. The other is about the objective function, and then there are number of instrument nodes applies that we have 2x plus y is greater than 200, like here. It should contain at least 200 instrumental nodes. So one of the constraints was this. The other constraint was 300. So this, the condition is about the number of nodes comprising of 200. You have to read the whole question as plays a total of 2 nodes. So we have each violinist plays a total of 2 notes, and each bassoonist plays only 1 note. So now bassoonist is in this case 1, and violinist is in x, so we can have as 2x, and it is greater than. To make sure that should contain at least 200, so it's greater than or equal to 200. And then for the next part, we have you have to decide on a minimum of 300 notes where each bassoonist will sing 3 soprano notes. So we have 3, 1. And again, the violinist will be playing 1 note, only 1 soprano note, so it's greater than 300. So they say that it is a little tricky, and such problems require a bit of practice. Now let's just move on to a table where we will assume, and you always have this basic assumption. So how to make this feasibility region? Again, we already know that y can be expressed in terms of x, but if we take x as 0 in this case, so we can have y as 200, you can see that this is 200. And then x for that part can be 100. Now this is one line drawn. For the next equation now, y is 100. Here it's 100. And then x is actually 300. So like this, you see, it's 300. So 2 lines drawn together, and one point of intersection is B. Now again, there's another constraint, because we are going to be solving this once we have the values for y and x. And there's this constraint that 3x minus y is greater than 0. So again, y can be, in this case, if x is 0, you can just simply have that as a minus value as well. So it can just simply go down as well. But there's no intersection for that part, and then you can have, if y is 0, you can just simply have x at that point, anything just divided by, on the other side with 3. That would be just, again, in terms of this equation that we had. This one, this equality that we had, less than 3x. So we're going to be focusing through simultaneous equations how to find out the values. In this case, we can just simply put in one. Look at just this table. We have one part, and we can have a simple part where we don't have to have too many complicated figures. So let's just say that we have one equation and we have the other equation. We don't have to multiply it with any number. We can just simply subtract them to cancel out the y, and then we can just have 5x, just adding them, and this will be 200. So then you can have 40 for x, in this case because y was cancelled. As you can see, you can just simply add them together, 5x, and this is 200, so is 40 for this. And then similarly, you can find by putting values here. So 2 into 40 plus y is equal to 200, so it is 80, and 200 minus 80 would yield 120, so that would be the value of y. So you found out one coordinate, and then you put both the values in this constraint. So 200 into 40, and then 400 into 120, and you get 56,000. Let's look at the other situation, where we have, okay, now in this part we have 2x plus y is equal to 200, and then we have again this part to find out what is the value of either of those. So now if you see that we can either multiply this equation with 2, or we can multiply this with 6, and just multiply this with 3. So or just you can see that if you multiply, cancel out the y, so multiply this entire equation with 3, so 6x plus 3y is 600. Now you can subtract the lower equation, so it's going to be 6x minus x would be 5x, and this would cancel out, and this would be 600 minus 300 would be 300. So 5x is equal to 300, then x would be, again, 5, 6 are 30, 60. Putting value as 60 would be 120, and then you can simply subtract 120 from 200 and you get 80 for this one, and you can just have this value as 44,000. You can have many other values as well, but then the feasibility region would exceed the value that we already have as minimum, and we don't want that. Now see where we already expect that y is 0, we can have x as 300 in this case. You simply just put y as 0, and we can have x as 300, because if we have x as 0, then y can be again 100, we already found that out. So for this, you just simply assume one as 0, the other as, so this can also give you some value for this. But if you have y, then that is already 100, and you can just simply place y as 100. That would be, again, this is 0, so that could also be giving you one other solution for that. Y is 100, and then you can have no c. So you can, I expect that you draw a point D as well in this case. So what is the value that you can derive by placing x as 0 in this case? So, but looking at this part, that you can know that y is less than 3 of x. So you have to know that it has to satisfy this equality. If you place x as 0, then it will be very complicated, because we're not sure whether we can satisfy this equality. So it is better not to go too much into complication of assuming x as 0, because if x is 0, then naturally y has to be 0. It can't really solve, we can't really satisfy this condition. So we would avoid using x as 0. So for having this, now we have already assumed that x can have various values. For this equality, at least, I can say that if x has some value, this will give us 60,000, but we're not going to be accepting this point, because we have this b as the minimum cost. So this, they say there's a wasteful value anyway, because this is not feasible solution for us. It's not practical. Now you just have to answer a few questions, and we can just do a bit of questions in the next lecture. Just revise this if you have any questions. So you can just put that down in comments, and I'll be glad to answer them for you. And now I'm, reaching the ending part of my lecture. Let's just see you next week, and thank you all. Good morning, class. This is your instructor. I'm going to be doing questions from two exercises today. Exercise pertaining to section 5.1 and exercise pertaining to section 5.2. So the format would be beginning from the easiest questions and then going about doing some tricky questions for you to basically grasp your concepts on feasibility region, a solution set, and graphical analysis in order to determine the profit maximization through the constraints system of problems that we'll be having, and drawn in close comparison to the examples that are given in the chapter. Exercises are very similar to those questions, so I would recommend that you first of all look at the example so that you can just then go about doing the questions. So that would also enable you to transition on towards the simplex method, maximization and minimization problems. Other than that, you can also see this board. We'll be doing questions from there. And the book is, I'll reiterate, by Stefan, Waner, and Stephen Costinoble. This is Finite Mathematics, and latest edition will be preferable. So let's just begin now. Okay, class, let's begin with the questions now. This is exercise 5.1. You can see this is question 3. So I have to write it down because somehow it's not able to copy to the Word. This is minus x minus 2y less than or equal to 8. So I'm just going to copy it. Minus x minus 2y is less than or equal to 8. We first of all keep x as 0, and then we can have the value of y, which would be again equal to, in this case we are going to be changing the whole into an equality in order to find out the value of y, which is minus 4 in this case, because the negative sign is going to go on towards the other side. We are going to keep in the next step, this is the first step, and the next step what we are going to do is keep this side as 0, and then the value of x would be equal to minus 8. Now why it's like that? Because we have y as 0. Now I'm going to be drawing the graph. If you can just simply see, the simplistic kind of a graph would have x as minus 8, right? So this is going to be, let's just put a limit to this, is just minus 8, and that would go beyond towards minus 4 as y. Now these are our coordinates, whether we can have as 0 or 0. This is a test point for our solution set. So now, okay, let me just join these two regions together. Okay, here we go. Here. Now, as we know the condition to determine the solution set, we have to place both the, replace both the variables with 0. So in this case, 0 minus 0 would be less than or equal to 8, which is primarily true because 0 is less than or equal to 8. So in this case, it is basically less than 8. So that means we can include the point of origin, and this would be our solution set. However, this part, which is extending down and going, like here, so this would all be the gray area. And the gray area, we can't really define how much to exclude in this case. So this gray area would be the unbounded region. Unbounded because we can't determine how much to exclude. So this is going to be an unbounded region. Now I'll take new questions. So this I have to clean the board. Okay, class, now if you see the next question, which is minus x plus 2y greater than or equal to 4. Minus x plus 2y is greater than or equal to 4. In this case, as you can see that y could be, and let me just put this as minus x plus 2y, equal to 4 in this case. So now if I place 0 here, so in this case y would be equal to 2 and x would be equal to, going by the same logic, minus 4. Now let me just draw this and also figure out at the same time whether we can have the point of origin included. So if you see that in this case 0, 0 cannot be our coordinates in this case, because if you place 0 here and 0 here, cannot, 0 plus 0 does not give you 4, and it is definitely not greater than 4. So then when we draw the graph, so it's just drawing out. Now we have x as minus 4, this is minus 4, and we can have y as 2. So now this is somewhere 2, right? So I'm going to be joining these two, together. And since this is not, the point of origin cannot be included, in this case, our solution set would be lying somewhere outside of this limit. Okay, so this would be again the unbounded region, and this is because we can't really know what to keep and put a limit on that, and we cannot, since include this part, this cannot be a solution set for us. So our solution set is primarily lying somewhere around here. It's also important for you to know that since it's not entirely enclosing our solution, so this is also known as the unbounded region, and this would include extending down and putting a limit. All this region would be unbounded, and this is where our solution set would be lying. So that would be the gray area, and that will be the white or the blue area, whichever that you prefer. Now let's just attempt a descriptive problem from section 5.2. Oh, class, there's another question that's a bit different. I would like you to see. This is question 15, 17. So I'll just do the later one. You can do the former ones. X plus y is greater than or equal to 5, and x is less than 10, y is less than equal to 8, where x is greater than equal to 0 and y is greater than or equal to 0. So now if you see that this part has already given to you the limit where y could be 5 and x could be 5, and since both can be, so let's just see that this assumption that both are greater than 0, automatically you put the limit that it cannot include the negative region. So whatever this part and whatever this part is, so, and beyond as well. So this region, which is below 0, basically, we're just not going to be, extending too much into it. Going towards, the graph, you can see that this is gray area, and since we're going to be taking everything above 0, so we'll be considering the point of origin in this case just 0, 0. So automatically we don't have to do the other test. So x is 5 and y is 5. As you can see that x is 5 in this case, or let me just put x as 5 here and y as 5 here, right? Now x is less than or equal to 10. Again, x could be, that was the first constraint. This is x can be 10, and where y at this point is it can be 8. So now this is 8. Let's just see, this is 8. Okay. So now if I just join it here, so you can see that this is like this. So we can have the solution set, because since the limit has been imposed that x and y can maximum, be, they have to be equal or greater than 5. Had it been less than 5, we would have included this region. But since now this is going to be our solution set for this question, because as you can see, we can't include this region, and that the constraint is that of greater than. So we have to choose at least this value and above, and this value and above. I hope you can understand this question. Okay, so now this whole value. Okay, so that we are going to be also taking this part and all this. This is all our region, but this part we are not going to be taking. Okay, class, this is a big question. I can't really copy it, so I would expect you to read it from here. This is question 26, resource allocation. Particle Institute of Technology's Math department offers 2 courses, Finite Math and Applied Calculus. So each section of Finite Math has 60 students. So we're going to be taking, Finite Math as X rather than the students. So for Finite Math, it's X, it's X, okay. And it says it has 60 students, and each section of applied calculus has 50. So the department is allowed to offer a total up to 110 sections. So now we have 2 classes where there are different sections. One is X as Finite Math, and the other is Y, which is the calculus part, and this is less than or equal to the total number of sections, which are 110 in this case, as you can see. So I'm going to be writing 110. So you can just base the assumption here that X is Finite Math and Y is your calculus, okay, so that you don't forget. Sorry, this marker is not writing very well. Suppose the university makes a profit of 100. Okay, so there's another condition now. Furthermore, than 6,000 students want to take a math, no more than 6,000 students want to take a math course. So again, there's a constraint of, we can say less than or equal to 6,000. So we're students of Finite Math, so we have 60x, this is the second constraint, plus 50y, okay, because section of Applied Calculus has 50. So now we'll have 50y, which is less than or equal to 6,000, because we don't want, or no more than 6,000 students will be, participating in these courses. And now suppose the university wants to make a profit of 100,000 on each section of Finite Math and 50,000 on each section of Applied Calculus. So it means that for the equation of the profit, it says that the profit is the difference, the profit is the difference between what the students are charged and what the professors are paid, actually. So now this again, I would be keeping it a bit simple. The first would be on each section of Finite Math, so it's going to be $100,000 of X plus $50,000 of Y. $50,000 of Y. This is going to be the profit function. I would want to determine the values of X and Y, and then we'll put those in the profit function in order to determine which combination of having this section as well as the students would give us the max profit, right? So in this case, the first part is that both of X and Y, our assumption is that they have to be greater than 0, so that we can go on with the problem, because for the solution set, it is the condition that there have to be some student, and this is the basic assumption, that there has to be some students in order to take a course. Otherwise, if there is no student, then we won't be having the classes in the first place. So whatever the solution set would be, it will first of all have the graphs. So beginning from here, so that means we would be nullifying this region, okay? This will not be part of the solution set. And now we have x and y is less than 10. That means that either x can be 10 or y can be 10. So this is 110, this is 110. This is our first equation. And you can just simply convert them to, like, you know, x plus y equal to 110. And that will be equal to 6,000, right? So, or let me just simply directly write it as, so that this is just paucity of space here. Okay, now that's fine. Okay, now this is the first part. Now the second part, you can see that if I keep y as 0, then x would be actually, you know, having 100 value. So the first, you know, coordinate could be 0 if x could be having 100 value, where y can be 0. This is the first step in this case. As you can see, you divide it by 16, it renders 100. On the other hand, if I keep x as 0, then I can have the value of y as 120. Because you divide 5 by 600, because 0 would be cancelled, so you get 120, right? So this would be 120. So the maximum that y can reach in this case is 120, and x can reach as 100, like this, 100. So in this case, you can see this is the point of intersection here, and our solution would rather be, you know, within the intersection part, this part, this and this. So you can just simply draw this, and this would be the gray area in this case, the gray area. This would not be included in the solution set because of the constraint that x plus y have to be equal to 110. So even though we have y as 120, we can't keep it because we can't go beyond 110 in this case, and we can't go beyond 110. So in this case, we had to have y as 0, then we can have 100, and x cannot be more than 100 in this case. It can basically, you know, either be 110, but if there is some value of y, then it cannot be more than, you know, both of them cannot be more than 110 in this case. So therefore, y, if it has some value, then we have to, you know, subtract that from the value of x. Okay, class, now I'll be going towards the other coordinate, which is 110 for both of them. So can we keep x as 0 and y as 110? Y as 110, but we can't really keep x as 110 and y as 0, because this would be incorrect and this would also be incorrect, because we can't really have 120 and we can't have x as 110 because we have already determined that x is 100, right? So then the third part, so we can only have this as feasible solution, which is A. Then we can have both of them as 0, 0, which is okay. Class, there was an interruption. So now as you can see that this is we cannot have x as 110 in this case, so we are going to be crossing this out. We're going to be crossing that part out as well. So now we can have this as A and this as B, and we can also have a third solution for, you know, including this. If you want to solve through simultaneous system of equations, let me just see if I can write this down. 60x plus 50y and x plus y is equal to 110, and this is 6,000, right? So now if you can just simply cut y by, you know, multiplying this whole equation by 50, so this would automatically be cancelled out, right? This is not writing very well. So yeah, class, we can just deduct or cancel them out, right? And we can multiply this whole equation by 50. So this was also 50. This was 50, and then we can subtract both of them. So there was a sign. So now this was also 50, and you can just simply multiply that with each other. So let me just calculate that for you. Well, class, now you can see that I have to go towards the calculator now. So what was the value initially? This was, if you can see the constraints, these were the constraints. I'll just zoom it out for you. So this was 110 with 50, and now you can just simply focus, and then we had 50x subtracted from 60. So now let's just move towards the calculator, and we can have 110, as you can just simply see it here, 110 into 50, and it approximately gives you 5,500, right? Now let's just move on towards the problem. So now 5,500, and that, let me just zoom, by, this is actually 10x. So we would be actually having x as divided by 10, right? So, but before that, as you know that we have this value as 6,000. So the value should be reduced to, from 6,000, 5,500 would actually give us 500, right? So now I'm just going to be directly writing 500 here, right? So 500, and then you can have just this included 50, and this would just give you the value of x. So x in this case is 50. Now what would be the value of y in this case? So you now put in the value of x in this equation. So we have 50 into 60. So, you know, if you put the value of x here in this whole equation, so you have 50 and 60, that will give you 3,000. And then plus you had 50y, and equal to 6,000. So now this 3,000 would move towards the other side, so you get about 3,000 in this case. I'm just going to be rewriting this equation here as 50y is equal to 3,000, right? Because we can have the value of x substituted as 50. So now you can have the value of y as 300 by 5, and we can have it as 60. So now the remaining coordinate that we'll have is 60, right? So now this 50 and 60 would give us the value in the main profit function of, you can just simply divide this by 1,000, you know, so just you can, so that you can just have this, and then you can just simply later express it as the whole figure. So for the profit function now, you can substitute all these coordinates. So in this case, this is the first coordinate, this is the second coordinate b, that was the first coordinate as 0, 0. The second is this one, and the third one was c, and d is the fourth one. So now you can just independently place values in the profit function, and in this case the profit function would be $100, 100x plus $50y. Okay, so now if I put the value 50 and 60, so $100 into 50 It's going to be giving us 5,000 here, plus 50 into 60, right? So now this is going to be giving us 3,000, and this is 5,000. Net would be 8,000 in this case. Now, can we have some function which is with a value which is greater than 8,000? Then you can just simply add the value of 100 perhaps as x. So you can have 6,000, and 6,000 will be equal to 6,000 in this case. So that is also lesser than this value. And you can have 110 as y in this case, you know. So so for the profit function now, let's just say for 100x, this is going to be 100 into 100x for the coordinate c. And this is going to give us, and where in this case y was 0, right? Y was 0 in this case, so we are going to be putting 0 here. That will give us 10,000. Now this 10,000 is actually greater than or 8,000 in this case, so we are going to be keeping this constraint as the most profitable for us. And okay class, so I thank you. I really would want you to, you know, okay, let me just give you a magnified look of this. I really want you to go through this, because there's, you know, not enough space for me to do it in you know, loose fashion. Kindly just look at this, and then we can, you know, approach other problems. If you have any problems, you can always reach back to me in comments. Thank you so much, class.